Every atom in our bodies, from the carbon that forms our very bones to the oxygen we draw in with each breath, was forged deep within the fiery heart of a star. Not a star still shining brightly today, but a star that completed its cosmic journey, that lived and died billions of years ago. This profound realization makes us, in the most literal sense, children of stardust, shimmering remnants of a universe that existed long before our own planet took shape. But have you ever paused to truly wonder what life was like for these magnificent cosmic parents of ours? What was the grand journey they embarked upon? And what incredible ends awaited them at the close of their stellar lives? Every night, as you gaze up at the vast, inky blackness punctuated by countless twinkling lights, you are witnessing the ongoing lives of billions upon billions of stars. Each one of those distant pinpricks of light is far more than just a distant beacon. It is a colossal powerhouse, an immense cosmic furnace where the very elements fundamental to our existence were created and refined through conditions that are almost beyond our comprehension. Yet, beneath that seemingly eternal and serene beauty lies an incredibly dramatic story. It is a narrative of violent births, brilliantly shining youths, periods of stable maturity, and then the most spectacular deaths the cosmos has ever orchestrated. From the gradual fading of smaller stars to the cataclysmic explosions that can briefly outshine an entire galaxy, these stellar lives leave behind the universe as most enigmatic and exotic remnants, rapidly spinning neutron stars, or the light-devouring mysteries we call black holes. Today, we are going to embark on this utterly mesmerizing journey together, exploring the entire life and death cycle of stars. We will delve into the profound physical laws that dictate their fates, discover how we can predict a star's future simply by understanding its size, and uncover the astonishing truth that the death of one star is in fact the very genesis for new life. This isn't merely a science lesson. It is a profound narrative of continuous creation and destruction, an epic saga of matter and energy recycling throughout the cosmos. It's a story in which we, as beings intricately woven from stardust, are an inseparable part. Prepare to expand your understanding and perspective on these cosmic fires that have birthed and continue to sustain everything we know and everything we are. How does this revised introduction feel? I've aimed for a more evocative and detailed approach, using language and pacing designed to draw in an American audience for that estimated 7 to 10 minute segment. Every single brilliant star we see in the night sky, from our familiar sun to those distant beacons, thousands of light years away, began its existence in a truly unfathomable place, within immense giant molecular clouds often simply called stellar nurseries. Imagine a vast, cold, dark cloud of gas and dust stretching for tens, even hundreds of light years across the emptiness of interstellar space. These aren't the fluffy white clouds you see drifting across Earth's sky, or even the turbulent storm clouds that bring rain. These are unbelievably tenuous regions of matter, so sparse that if you could actually step inside one, you'd feel nothing but an almost absolute vacuum. Yet, it's precisely within this seemingly empty, almost infinitely cold expanse, where atoms barely vibrate, that the seeds of a star's life quietly begin to germinate, set into motion by an unseen yet profoundly powerful force. That force, the ultimate architect of cosmic structures, is gravity. Within these colossal clouds of gas and dust, there are always some regions where the density of matter is just a tiny bit higher than its surroundings. Perhaps a shock wave from a nearby supernova explosion rippled through, compressing a pocket of gas. Maybe the smaller clouds gently collided, or simply a random fluctuation in density occurred, creating a pivotal starting point. At this crucial point, gravity begins its relentless work. It inexorably pulls these minute particles of gas and dust closer together, little by little, like an invisible, colossal magnet slowly drawing in tiny specks of metallic filings. As matter relentlessly continues to fall inward towards the center, this vast cloud begins to collapse under its own immense weight. This ongoing collapse causes the matter to become increasingly concentrated, its density skyrocketing at an astonishing rate, and, as the fundamental laws of physics dictate, when matter is compressed, its temperature rises dramatically. This collapsing, increasingly hot, and dense region is what scientists refer to as a protostar. Think of it as an embryonic star, growing rapidly within the cosmic womb. It isn't yet glowing fiercely like a true star, but deep within its core, pressure and temperature are relentlessly building, awaiting that epic-making moment of its birth. The protostar's collapse continues for hundreds of thousands of years, sometimes stretching over millions of years, an incredibly slow dance from a human perspective, but a relatively swift one in cosmic terms. The protostar steadily grows hotter, denser, and the pressure at its core escalates to unimaginable levels. Finally, at the very heart of this protostar, the temperature and pressure reach an absolutely critical and extraordinary threshold. Approximately 15 million degrees Celsius, about 27 million degrees Fahrenheit. At this point of immense heat and staggering pressure, the hydrogen atoms are squeezed so tightly together that they are no longer merely individual atoms. Their nuclei begin to collide with such incredible force that they overcome their natural electrostatic repulsion and fuse together for hydrogen nuclei, smash and combine to form a single helium nucleus, unleashing an absolutely staggering amount of energy. This process, known as thermonuclear fusion, is the very engine of a star, and it's governed by Einstein's most famous equation, E=mc. This moment, when fusion ignites, is when a star is officially born. Once thermonuclear fusion erupts in its core, the newly born star immediately generates an immense outward pressure, known as radiation pressure. This pressure, originating from the energy released by the nuclear reactions, pushes matter away from the core. The truly miraculous aspect is that this outward radiation pressure perfectly balances the inward pull of gravity, which is constantly trying to crush the star. This exquisite and delicate equilibrium between gravity's relentless attempt to collapse the star and the fusion pressure as outward push is what sustains the star. For the vast majority of its existence, it allows it to shine steadily for millions, even billions of years, in a phase astronomers call the main sequence. This is when a star truly becomes a brilliant beacon, ceaselessly generating energy, illuminating the vast darkness of the universe, and embarking on a long life filled with incredible transformations yet to come. Once a star successfully ignites thermonuclear fusion in its core, it enters the most significant and often longest phase of its existence, the main sequence. This is the stellar equivalent of adulthood, a period of remarkable stability and consistent energy output for billions of years. A main sequence star like our own Sun is in a delicate, almost perfect, cosmic balancing act. We learn how gravity is constantly trying to crush the star inward, relentlessly pulling every atom towards its center. But at the very core, the powerful outward pressure, generated by the continuous fusion of hydrogen into helium, perfectly counteracts this gravitational squeeze. It's this intricate equilibrium that allows a star to shine steadily, predictably, day after day, year after year, illuminating its planetary system and providing the energy needed for life, as we know it, to potentially flourish. Our Sun, a typical yellow dwarf star, has been comfortably nestled on the main sequence for about 4.5 billion years and is expected to remain there for roughly another 5 billion years. During this immense span of time, it will continue to fuse hydrogen into helium, acting as a stable, predictable energy source. But not all stars are created equal, and their time on the main sequence varies dramatically depending on one critical factor: their initial mass. This is perhaps one of the most counterintuitive concepts in stellar evolution, so let's explore it carefully. Consider the smallest stars, the so-called red dwarfs. These stellar midgets can be as little as 7 to 8% the mass of our Sun, though they still possess enough heft to ignite fusion. Because they are so small, their gravitational pull is weaker, and consequently, the pressure and temperature in their cores are much lower. This means they burn their hydrogen fuel incredibly slowly, like a tiny candle flickering almost imperceptibly. Red dwarfs are the ultimate cosmic marathon. Runners, they can remain on the main sequence for hundreds of billions, even trillions of years. To put that into perspective, the universe itself is only about 13.8 billion years old. This means that every single red dwarf star that has ever formed in the universe is still alive and well on the main sequence today. They are the true energy misers of the cosmos, quietly burning their fuel with astonishing efficiency. Now, let's look at stars with a medium mass, like our Sun. These stars are more substantial than red dwarfs, but nowhere near the giants we'll discuss next. Their internal pressures and temperatures are higher, leading to a faster rate of hydrogen fusion. Our Sun, for example, will spend a total of about 10 billion years on the main sequence. It's a respectable lifespan, certainly long enough for complex life to evolve on a planet like Earth. These stars are common, stable, and play a crucial role in the development of planetary systems. But then we come to the true titans of the stellar world, the massive stars. These giants can be 10, 20, even 100 times the mass of our Sun. With such enormous mass comes an incredibly powerful gravitational pull, which in turn creates immense pressure and scorching temperatures in their cores. Unlike the frugal red dwarfs, these behemoths consume their hydrogen fuel at a truly furious rate. They are like cosmic sports cars, burning through their tanks at an astonishing pace. A star 50 times the mass of the Sun might only live for a few million years on the main sequence. Their lives are short, but spectacularly brilliant. They shine with an intensity that can dwarf entire solar systems, outshining thousands, even millions of their smaller main sequence counterparts. While they live fast and die young, their dramatic existence is absolutely crucial for the universe. As we will soon discover, regardless of their size, a common and profoundly important process is occurring within the cores of all main sequence stars. The formation of new elements. This is the fundamental alchemy of the cosmos, as hydrogen atoms are fused into helium. The star is slowly, but surely building heavier elements. For most of a star's main sequence life, it's primarily fusing hydrogen into helium. But for massive stars, and even towards the later stages for Sun-like stars, the processes begin to lay the groundwork for more complex element creation. The energy released from these fusion reactions is what provides the light and heat we observe, radiating outward through the star's many layers and eventually into the vast emptiness of space. This long, stable period is when a star fulfills its primary purpose, to be a steady source of light and energy, and to slowly, meticulously, build the very building blocks of the universe within its fiery heart. Every star, no matter how grand or how small, eventually faces the inevitable truth. Its fuel supply is finite for stars like our Sun, and indeed for all stars with similar or smaller masses. The end of the main sequence isn't a sudden, cataclysmic explosion, but rather a more gradual, drawn-out transformation. It's a cosmic fading, a slow shedding of layers before finally settling into a quiet retirement. The beginning of the end for these stars arrives when the supply of hydrogen fuel in their core finally dwindles to a critical low. Imagine a campfire. As long as you keep feeding it logs, it burns steadily and brightly. But what happens when the logs run out? The flames might diminish, but the embers still glow, intense and hot. Similarly, when the hydrogen in a star's core is nearly exhausted, the primary fusion reactions that sustain it for billions of years start to falter. The delicate balance between the outward pressure of fusion and the inward pull of gravity is disrupted. With less outward pressure, gravity begins to win the battle, causing the inert helium-rich core to start contracting inward. As this helium core shrinks, it heats up dramatically due to the immense gravitational compression. While the core itself isn't hot enough to start fusing helium just yet, the layers of hydrogen surrounding the contracting core become incredibly hot and dense. Here, in a shell around the dying core, the remaining hydrogen ignites, fusing with an intensity even greater than before. This phenomenon is called shell hydrogen fusion. The sudden surge of energy From this shell, fusion pushes the outer layers of the star dramatically outward. This expansion is massive, causing the star to bloat into a colossal, diffuse ball of gas, cooling significantly as it expands and turning a deep, fiery red. This new, expanded phase of a star is known as a red giant. Our own sun, in about 5 billion years, will undergo this exact transformation. It will swell so enormously that its outer layers are predicted to engulf and vaporize Mercury, Venus, and potentially even Earth. Imagine looking up at a sky dominated by a sun so vast and red it fills half the visible heavens. A chillingly beautiful spectacle signaling the end of our planetary system as we know it. The red giant phase can last for hundreds of millions of years, as the star continues to burn hydrogen in its shell, and sometimes for slightly more massive stars, even begins to fuse helium into carbon and oxygen in its very center. After the red giant phase, the star has used up most of its available fuel, and the outer layers become loosely bound. The intense radiation and stellar winds from the core gently, but consistently, push these outer layers away into space. This isn't an explosion, but more like a cosmic exhale, a shedding of old skin. As these layers drift away, they form incredibly beautiful, often symmetrical, and vividly colorful expanding shells of gas and dust known as a planetary nebula. Despite the name, these nebulae have absolutely nothing to do with planets. The term planetary was coined by early astronomers who thought these round, disk-like objects resembled planets. Through their rudimentary telescopes, these nebulae are among the most stunning objects in the night sky, vibrant testaments to a star's peaceful departure. They are the star's last artistic masterpiece before it fades from view. What remains after the planetary nebula drifts away is the super-dense, extremely hot core of the star. This stellar remnant is called a white dwarf. It's remarkably small, roughly the size of Earth, yet it contains the mass of an entire star, like our sun. Think about that, packing the mass of something 330,000 times heavier than Earth into a sphere the same size as Earth. This makes white dwarfs incredibly dense. A single teaspoon of white dwarf material would weigh tons, perhaps even more than a large truck. A white dwarf no longer undergoes any fusion reactions. It's effectively a cosmic ember, radiating away its residual heat, and slowly, glacially, cooling down over billions and trillions of years. Eventually, after an unimaginable amount of time, it will cool completely, becoming a theoretical object known as a black dwarf, a dark, cold, and utterly invisible chunk of carbon and oxygen drifting through the emptiness of space. The fate of these stars is governed by a crucial cosmic speed limit known as the Chandrasekhar limit. This limit, named after the brilliant astrophysicist Subrahmanyan Chandrasekhar, states that a white dwarf cannot be more massive than about 1.4 times the mass of our sun. If a star's core at the end of its life is more massive than this limit, the electron degeneracy pressure that supports a white dwarf against gravitational collapse is simply not enough, and that leads us to the far more dramatic and violent ends awaiting the truly massive stars, events that shape the very fabric of our universe. While the smaller and medium-sized stars like our sun gracefully shed their outer layers to become white dwarfs, the fate of truly massive stars is far more dramatic, even cataclysmic. These are the giants of the cosmos, stars that began their lives with at least 8 times the mass of our sun, often much, much more. Their immense size and gravitational pull lead to an entirely different and utterly spectacular end. For these stellar titans, the dying breath is not a gentle sigh but a furious roar, a cosmic explosion known as a supernova. Remember how stars fuse hydrogen into helium in their cores? For massive stars, the process doesn't stop there. Their enormous gravity creates such intense pressures and temperatures at their cores that they can continue to fuse progressively heavier elements. Once the hydrogen is exhausted, they begin to fuse helium into carbon. When the helium runs out, they fuse carbon into oxygen, then oxygen into neon, neon into magnesium, and so on. This process continues in a rapid, almost frantic succession, creating layers of increasingly heavier elements like a cosmic onion. Each new fusion reaction requires even higher temperatures and pressures than the last, and each stage is significantly shorter than the one before it. A massive star might spend millions of years fusing hydrogen, but only a few hundred years fusing silicon, and a mere matter of days fusing oxygen. This relentless chain of fusion continues until the star's core is finally composed almost entirely of iron. And this is where the cosmic tragedy truly begins. Iron is the ultimate breaking point for a star. Unlike all the lighter elements, fusing iron atoms together does not release energy. Instead, it actually consumes energy. It's like trying to get a fire to burn by pouring water on it. When the core becomes iron, the star can no longer generate the outward pressure needed to fight against its own overwhelming gravity. The core, now entirely made of iron and unable to produce energy, has lost its battle. In a horrifying instant, with no outward pressure to support it, the iron core of the massive star begins to collapse catastrophically. This collapse is incredibly swift, occurring in mere milliseconds. From a size larger than Earth to something no bigger than a city, the outer layers of the star, which are still fusing elements and haven't yet received the memo that the core has given up, come crashing down at an astonishing fraction of the speed of light. They smash into the now unimaginably dense, unyielding iron core, which has become as stiff as a bowling ball. This impact creates an enormous shockwave that rebounds, or bounces, off the supercompressed core. This rebounding shockwave then rips violently outward through the star's outer layers, which are still falling inward. The sheer force of this outward blast, combined with an intense burst of subatomic particles called neutrinos, propels the star's entire outer envelope into space in a truly spectacular and unimaginably powerful event, a supernova explosion. For a brief period, perhaps a few weeks or months, a single supernova can shine brighter than an entire galaxy of billions of stars. It's a cosmic fireworks display of unparalleled grandeur, visible across vast stretches of the universe. But the supernova is far more than just a beautiful, albeit violent, light show. It is the ultimate cosmic crucible, the most fertile ground for the creation of new matter. All the elements heavier than iron, including gold, silver, uranium, and all the precious metals that enrich our planet, are believed to be forged during the extreme conditions of a supernova explosion. The intense temperatures and pressures generated during the collapse and subsequent rebound force atomic nuclei together in ways that are impossible under normal stellar fusion. Then, these newly created heavy elements, along with all the lighter elements that the star had produced throughout its life, are scattered throughout the universe by the force of the explosion. These expelled materials enrich the interstellar medium, providing the raw ingredients for future generations of stars, planets, and even life itself. Without these violent deaths, the universe would be a much simpler, less interesting place, devoid of the complex chemistry necessary for planets like Earth and beings like us. We are, in a very real sense, the direct product of these titanic stellar explosions. When a massive star detonates as a supernova, it might seem like the ultimate cosmic curtain call, the complete annihilation of a celestial giant, but often, the story doesn't end there. What remains of the star's core after the colossal explosion determines its final, incredibly exotic form. These are the dense, often bizarre, cosmic remnants that represent the ultimate triumph of gravity. Let's consider the first possibility, the birth of a neutron star. If the core of the star that just went supernova has a remnant mass between roughly 1.4 and 3 times the mass of our Sun, it won't collapse all the way into a black hole. Instead, the crushing force of gravity is so immense that it compresses the protons and electrons in the core into an entirely new type of particle, neutrons. Imagine a force so powerful it literally squashes atomic structure out of existence. The entire core becomes a super dense ball of neutrons, held together by a force called neutron degeneracy pressure. The result is truly mind-boggling. A neutron star is incredibly small, typically only about 12 to 15 miles across, roughly the size of a metropolitan city like San Francisco or Manhattan. Yet, it packs the entire mass of 1 to 3 suns into the tiny sphere. To give you a sense of this incredible density, consider this. A single teaspoon of neutron star material would weigh billions of tons here on Earth, equivalent to the weight of Mount Everest or even more. They are the densest objects in the universe that we can still directly observe. Neutron stars also spin incredibly fast, often hundreds or even thousands of times per second, and some emit beams of radiation from their magnetic poles. When these beams sweep past Earth like a cosmic lighthouse, we detect them as regular pulses, and we call these specific neutron stars pulsars. They are a captivating testament to the extreme conditions left behind by a supernova. However, there's an even more extreme outcome for the most massive stars. What happens if the core left behind after the supernova is even heavier? If the stellar remnant's mass exceeds approximately 3 times the mass of our Sun, then even the immense neutron degeneracy pressure isn't enough to withstand gravity's relentless pull. At this point, no known force in the universe can stop the collapse. The core continues to shrink, relentlessly, beyond any comprehensible limit. This leads to the formation of the most mysterious and enigmatic objects in the cosmos, black holes. A black hole is not an empty space, but rather an incredibly compact region of spacetime, where gravity is so overwhelmingly powerful that nothing, not even light, can escape its grasp once it crosses a boundary known as the event horizon. Imagine trying to paddle upstream on a river that's flowing faster and faster. At a certain point, the current becomes so strong that no matter how hard you paddle, you can't move forward. You're pulled inevitably downstream. The event horizon is the point of no return for light and matter. Anything that falls across it is gone forever, swallowed by the black hole. At the very center of a black hole lies a singularity, a point of infinite density where all the mass of the black hole is theoretically concentrated, and where the laws of physics as we understand them break down entirely. Black holes come in various sizes, from stellar mass black holes, which are the remnants of massive stars, to supermassive black holes found at the centers of nearly every galaxy, including our own Milky Way. These colossal black holes can have masses millions or even billions of times that of our Sun, influencing the dynamics of entire galaxies. Despite their name and the popular imagery, black holes do not suck things in from vast distances. Their gravitational pull only becomes extreme at very close proximity, just like any other massive object. However, once you cross that event horizon, your fate is sealed. The very concept of a black hole continues to challenge our understanding of physics, pushing the boundaries of what we thought possible in the universe. They are cosmic enigmas, a testament to gravity's ultimate power, and a constant source of fascination and ongoing research for scientists around the globe. We have now traveled the complete life cycle of stars, from their humble beginnings as swirling clouds of gas and dust to their spectacular, sometimes explosive, finals. We've seen how tiny red dwarfs quietly sip their fuel for trillions of years, how sun-like stars gracefully expand into red giants before gently shedding their layers to reveal a cooling white dwarf, and how the true titans of the cosmos end their lives in blinding supernova explosions, leaving behind super-dense neutron stars or the ultimate gravitational wells, black holes. But what is perhaps the most astonishing revelation about this entire cosmic drama is that the death of a star is never truly an end. Instead, it is always a magnificent new beginning. The material expelled from dying stars, especially the heavy elements forged in the crucible of a supernova, doesn't simply vanish. It is flung out into the vast emptiness of interstellar space, enriching the cosmic medium. These enriched clouds of gas and dust, teeming with carbon, oxygen, iron, and all the elements essential for life, will then, over immense spans of time, begin to collapse once more. Under the relentless pull of gravity, they will ignite, giving birth to new generations of stars, new planetary systems, and perhaps even new forms of life. This is the universe's ultimate recycling program, a grand, continuous cosmic ballet of destruction and creation. Consider this profound truth. Every single atom of carbon in your DNA, every molecule of oxygen you breathe, every speck of iron in your blood, and even the gold and silver that grace our planet were not created here on Earth. They were forged in the incredibly hot, dense cores of long-dead stars, or blasted into existence during the cataclysmic moments of a supernova. We literally carry the stardust of ancient cosmic events within us. We are, in every sense of the word, children of the stars. Our existence, our very being, is inextricably linked to the lives and deaths of these celestial giants that have blazed across the universe for billions of years. The study of stellar lives and deaths is more than just understanding distant astrophysical phenomena. It is about understanding our own origins, our place in this vast, evolving cosmos. It reminds us of the incredible scale of the universe, the immense power of its forces, and the intricate connections that bind everything together. From the most common atom to the most exotic stellar remnant, everything is part of an ongoing, endless cosmic cycle. As we continue to gaze at the night sky, we are not just looking at points of light. We are looking at the ongoing story of creation, a story in which we are both observers and participants. The universe is a dynamic, living entity, and the stars are its pulsating heart, eternally burning, dying, and being reborn, charting the course for all that is, and all that will ever be. If you found this cosmic journey through the life and death of stars as fascinating as we did, please consider hitting the like button right now. Your likes truly help our videos reach more curious minds across the universe, just like yours. And if you think your friends or family would also be captivated by these incredible stories of cosmic creation and destruction, don't hesitate to share this video with them. Every share helps us grow our community of space enthusiasts. We love hearing your thoughts and questions. So, what was the most surprising thing you learned today? Do you have any lingering questions about black holes or the future of our sun? Leave us a comment below. We read every single one, and your insights often inspire our next deep dive into the cosmos. Finally, if you're passionate about uncovering the universe's greatest mysteries, and you want to join us on future expeditions into the unknown, make sure to subscribe to our channel. And don't forget to ring that notification bell so you'll be the first to know when our next cosmic exploration begins. Thank you for watching, and we'll see you in the next video.